we saw last time is that there was a lot of work potential in the gases leaving the turbine. And so what we want to be able to do is to recapture that. And how can we effectively use that? Well, one of the things we could do, and we call it regeneration, is we can take the exhaust gases and have them heat up the air after it leaves the compressor and before it goes to the combustion chamber. So we're capturing that, preheating the air going into the combustion chamber. And this is called regeneration. So we want to use exhaust gases to preheat air to the combustion chamber. So we'll draw a diagram indicating this. So this is figure 1412. So if you want to see a nice version, look at figure 1412. If you want to see an accurate but less well-drawn version, you're seeing that right here. So you have the compressor, it's coming out of the compressor, and it's going to go into a regenerator. The regenerator is a heat exchanger. All it is a heat exchanger. So it's going to come out at state 2 and go in here. I'm going to have my turbine over here. So it's going to come out here, and so I have the turbine work going back. It's going to come out here and go back into the combustion chamber. And so this is coming out at X. I don't know what it is. It's going to come out of the combustion chamber at 3, come out of the turbine at 4, and it's going to go through the turbine, come out through the regenerator, and come out at 5. So this is a heat exchanger. It's maybe a fin tube heat exchanger, something like that, where the air going through the inside of the fin tubes, and the exhaust gas going over the other. There are a couple of different configurations for that. So this comes out at an unknown temperature, but a higher temperature. If I look at this on a TS diagram, going from 1 to 2, 2 to 3, but along the way, it goes to X. So first, it goes through the compressor, it's heated up from 2 to X, and then from X to 3, it goes in the combustion chamber and out of it, into the turbine. It comes out of the turbine at state 4, and then it goes through the heat exchanger to state 5, and then it exhausts at that point. And so what we're looking at is that, again, this area and this area are the same. So the heat given up here is the heat gained here. So we're looking at that. And so we have that m dot A times Hx minus H2 is equal to m dot A plus m dot F times H4 minus H5. And what we have, so what we talk about with a regenerator is we talk about a regenerator effectiveness. So it's the actual heat transfer over the max possible. And so this is going to be equal to Hx minus H2 over 1 plus RFA times H4 minus HC. And HC is the enthalpy of the products at T2. And so what we're going to do now is we're going to change this to C sub p's. So I have this is C sub pa times tx minus t2 over 1 plus RFA C sub pp of the products times T4 minus T2. Now in the text, when we do problems, we use PR ratios, something that we haven't covered. And what we're going to use in the next problem is ideal gas relationships, which we've done throughout this chapter. And this allows us to program this and do parametric variation, so I could vary things more easily and see what the effect is on the system behavior. So, and very often what we're going to do, just for the regenerator effectiveness, is that I'll probably let these be the same so they cancel out, and it'll make the regenerator effectiveness much easier to do. So now the problem that we want to look at, so we're going to be using this. We see we have an RFA and a TX in here, and we're going to end up having to get two equations with two unknowns and solve them, but on it goes. What we're going to look at next is problem 1425 at the back of the book. So again, 1425. 1425 has a lot of stuff in it, so let's look at this. So this is how I have it drawn. On different days, I draw the regenerator in different places. I don't know why. It goes through and goes out into the combustion chamber. This is a better way to do it. We have two turbines here. And so what's going to happen when I have two turbines is I have one turbine that drives the compressor and the other turbine that provides the power. So this is something they call dual shaft. They have a dual shaft in there, and one of the shafts drives a compressor and the other one is connected to your generator load. So we have a 20 megawatt load. In here I have WT is equal to WC. WT1 is this. And let's see what's happening here. So it goes in here. So I come out of here, state 1 to state 2 prime. And we're told here eta sub C is 85%. Oh, good grief, we have to deal with efficiencies again. Comes out of here at state X. Comes out of here at state 3. Comes out of here at 4 prime. And goes into the second one. Comes out of here at 5 prime. And it's going to go back to the generator, regenerator, and come out at state 6. And we're given the following information. T3 is equal to 1300 degrees K. R sub P is equal to 10. We often picked R sub P as 10 because it's a nice number, just like P0 is 100 instead of 101.3. It's an easier number to work with. P1 is 300. P1 is 100. There it is again, P1. And the regenerator effectiveness is 80%, which is on the high side, and eta sub T is 87%. So we have all this stuff. And now, let's look at what the TS diagram looks like. So the TS diagram is a little more complicated. So we're going to have the ideal compression 1 to 2. It's going to 2 prime. And then it's going through the regenerator to state X. So we have the ideal going to the actual to X. We're going to state 3. Expands ideally to 4. but we're actually going to 4 prime. And then, ideally, it was 5, but we're actually going to 5 prime. And then we're going down to 6, where it leaves. And that's what the TS diagram looks like. So we have this going up here, compressed, goes in there. It expands through the first turbine, actual state 4 prime. Then it expands through the second turbine, actual state 5 prime. It cools from 5 prime to 6 through the regenerator. The energy given up here is the same as the energy picked up here. And so that's what we're looking at. And now we're going to go through and find all the cycle's state points and do the analysis that we were supposed to do and all that sort of stuff. So that's what's happening next. So with their compressor efficiency, well, let me see. First, T2 is equal to T1 times R sub P to the K minus 1 over K. And so T2 is 579 degrees K. K is equal to 1.4. And A sub C is equal to 0.85 is equal to H2 minus H1 over H2 prime minus H1 is equal to T2 minus T1 over T2 prime minus T1. And with that, we come up with T2 prime to 628.5 degrees K. So I know what T2 prime is. P2 prime is equal to P2 is equal to 1,000 kPa. And so I can solve at this point for WC. WC is equal to H2 prime minus H1 is equal to C sub P 1.0047 times 628.5 minus 300, where I have that WC is equal to 330 kilojoules per kilogram.